Chapter 4, temperature. Okay, so what is temperature? It is written here. Temperature does not measure the amount of thermal energy in a body. So then temperature is what? So I put the definition here. Temperature is actually the degree of hotness of a substance. So that means it is how hot the object, but they never tell you how much energy is inside the object. So make sure you are clear on this. They tell you how hot is the object, but they don't tell you how much heat energy or how much thermal energy in the object. So then maybe you're wondering what term is used for the one that tell us the amount of thermal energy in an object. So that should be called enthalpy. Enthalpy tell you how much thermal energy in an object. Okay, so let's move on. This part. Two objects of different masses made of the same material at the same temperature would have different amounts of heat. We have different amount of heat. So that means imagine you have one big object and one small object. They are made of same material. Let's say they are made of copper. Okay, so the big one, of course, you should expect it has a lot of heat energy inside. The small one should have a little bit of heat energy inside. So logically should be like that. So imagine the big one and the small one made of same material, same temperature. Okay, but they have different size or different mass. So the amount for the amount of heat energy in the big object should be more. And the amount of heat energy for the small one should be less. So this thing we have to make ourselves clear first. Now, so we write down this one have more energy, and this one have heat, less energy. Okay, so next point, when a substance melts or boils, heat is input, but there is no temperature energy. Okay, so that means what they're trying to say is when you melt or boil a substance, the temperature remain constant. So we need to know about that. Temperature remain constant. So that means the input, the inputs of the heat to melt or to boil the substance, it is not used to increase the kinetic energy, but it is used to break the bond. Okay, break the bond, break the intermolecular forces. So this kind of idea. Now, thermal equilibrium. Thermal energy is transferred from a regions of higher temperature to a regions of lower temperature. So, okay, that means if you have two objects, so the first one has a higher temperature, which means hot, okay, and the other one is lower temperature, which is cold. So the hot objects will transfer thermal energy to the cold object. So they will transfer until thermal equilibrium. Thermal equilibrium means they will transfer the thermal energy until they reach the same temperature. Same temperature is the important point here. Okay, so a conditions when two or more objects in contact have the same temperature. So you can see there the important words, same temperature. which is here, same temperature. So there is no net flow of energy between them. Okay, so imagine, let's say I draw out. So you have one big object here and another small object here. So initially this is 100 degrees Celsius, and let's say this is 20 degrees Celsius. Okay, so what happened is the heat transfer keep happening, So until at the end, the two objects have the same temperature. Let's say this become 90, and this become 90 also. So there is a decrease of temperature for the 100 degrees Celsius big object, but the small object 20 degrees Celsius, it increases to 90 degrees Celsius. So when they both have the same temperature, that means they achieve thermal equilibrium. So when this happens, it doesn't mean that the heat stop flowing already. The heat is still flowing. It's just that the heat that flow to the small object is the same with the heat that flow to the big object. Same. Okay. So we call that no net flow of heat energy. So here NB is what? NB is note well that not equal internal energy. Okay, not equal internal energy, because number of molecules is unknown. So they are trying to say that they have the same temperature, they achieve thermal equilibrium, but it doesn't mean that they have the same internal energy. So let's revise back. What is internal energy again? So I write here, internal energy is the potential and kinetic energy. Potential and kinetic energy. So potential energy is like related to the spacings of the molecule, whether they are close or further apart. So that affect the potential energy. Kinetic energy should be easier to understand, how fast the particle move. Okay, so the total of potential and kinetic energy is the internal energy. So we have to say that when thermal equilibrium is achieved, the internal energy is not equal. What is equal is temperature is equal. Temperature is equal. So be careful for the thermal equilibrium here. Next point, regions of equal temperature are in thermal equilibrium. So the main concept is stated again, must be equal temperature. Then we call it thermal equilibrium. So 4.2, measuring temperature. A physical property that varies with temperature may be used for the measurements of temperature. So example, change in volume of a liquid or gas. So change in volume of a liquid or gas. So you can imagine the clinical thermometer. The mercury is inside the thermometer, so it expands. The volume expands because of temperature. Okay, so the mercury expand. So we are using the concept of V proportional to T. Okay, so the next one, change in pressure of a gas. So this one, imagine when the temperature is hot, then the pressure increase. Then they make use of the pressure to work to find out the temperature. So pressure is proportional to temperature. So they use pressure to work out the temperature. Now the next one, change in electrical resistance. Change in electrical resistance. How? Okay, so that means when the temperature is different, the resistance is different, and they use the resistance to find out the temperature. So I give you one example. So actually this example is somewhere in the past year question. So I just draw out the graph here for your reference. Okay, so I pull it down here. Okay, so we have a graph like this. The y-axis is the resistance. The x-axis is the temperature. Temperature in degrees Celsius. So the graph is like this. Okay, so how we make use of this graph? It is like this. You measure the resistance of the substance, and let's say you get a particular amount of resistance. Then you read the graph, bring it down, and you can find out the temperature. So if let's say the resistance change to another value, and then you read the graph again, then you bring it down to find out the new temperature. So from the resistance, we know the temperature. Okay? But the thing is, they are not proportional. They are not proportional. So not like the first and the second one, they are proportional. Proportional, you should expect directly proportional, something like this. V versus T, to be a straight line graph. This one you should expect P versus T to be a straight line graph also, because it is directly proportional. Okay, so now the next one, you see the notes again. Change in EMF of a thermocouple. Change in EMF. So EMF is like the voltage. Change in EMF. Okay, so I give you one example to let you imagine on how the graph looks like. So let's say this one, I draw out the graph here, is one of the past year question also. Yeah, this is the graph. So how to understand the graph? Similar to the third one just now, where you read the EMF of the thermocouple. Okay, thermocouple. You read the EMF of a thermocouple, and that means you are trying to find out the voltage. Trying to find out the voltage. So let's say the voltage is this value, and then you bring it down to read the temperature. Okay, so it's like that. And by the way, what is thermocouple? Of course, you have to understand that as well. So thermocouple, you may learn it before, or maybe you have no firm concept on that. So we do a quick revision on thermocouple first. Thermocouple, basically they have to use a couple of different metals, something like this. The basic one, let's say. You put a voltmeter in between. Okay, I put two container there. So the container is joined up with metal 1 and metal 2. Okay, now you put them in different temperature. Let's say you put it in this place with, okay, so of course you have to put inside the two different metal have to put inside the liquid, let's say. Okay, and let's say this is the boiling water, 100 degrees Celsius. 100 degrees Celsius. And then the other side, let's say you put in 0 degrees Celsius. So let's say ice water. So then you read the the voltage here, the EMF over here. And then from here, you can do a lot of calibrations. The details I just skip. Okay, so I just let you see roughly how it works. So it's like this. The basic structures of thermocouple thermometer is like this. Use two different metals and put in two different temperature to find out the EMF. Okay, so next one. Physical property should have the following qualities. That means you see you have four physical properties: volume, pressure, resistance, and EMF. So the properties is change in property with temperature should be large enough to be measured accurately. So that means change in 1 degree Celsius. Make sure that here the volume change big enough and the pressure change, there is a big enough change in pressure to be measured. There is a big enough change in resistance to be measured, or there is a big enough change in EMF to be measured. So if it's not big enough, then we can't detect the change, then that is not suitable. Now, value of temperature recorded should be reproducible. Reproducible, that means first time when you measure 30 degrees Celsius, you get 20 millivolt. Second time when you measure 30 degrees Celsius, make sure you get 20 millivolt again. Cannot be different value, and then that is not suitable also. So okay, here that means melting point should be the same when measured a second time. So this is another example. So the substance must have the same melting point. Okay, first time and second times when you measure it. So okay, then that is a suitable thermometer. Now let's move on. Okay, here property being used must be suitable over temperature range being measured. So temperature range, for example, like clinical temperature is 20 something to 30 something. That's the temperature range. Okay, so our let's say we are using mercury, we check the volumes of the mercury which expands in different temperature. So the expansions must be big enough to be seen, and we have to consider all those when you choose the suitable things. So we consider mercury because mercury is easy to see. It is not transparent, it's opaque. Okay, so next one. Should be able to be calibrated easily. Hence, property should change uniformly with temperature. So calibrated easily is like you set up the scale in the thermometer. Okay, so you can set up the scale that is doing the calibrations. Okay, so we have to set up the scale easily lah. We have to make sure this happens. So then it is suitable. Now, 4.3 thermodynamic scale. So thermodynamic Kelvin scale. So you already know Kelvin, right? Plus 273. But this chapter, be careful. 273.15. 273.15. Previously, if you put 273, it's okay. But for this chapter, they require a more accurate value, 273.15, to convert degrees Celsius to Kelvin. So only for this chapter. Okay, theoretical scale, that is independence of properties of any particular substance. Okay, so that is the Kelvin scale. So based on idea that average kinetic energy of particles of a substance increase with temperature, and the average kinetic energy is same for all substances at a particular temperature. So they are trying to say that the first point and the second point, which seems like a bit deep, and basically they are trying to say that temperature is proportional to kinetic energy. So the temperature in Kelvin is proportional to kinetic energy. So that means when the temperature is higher, kinetic energy is higher. No matter what substance is that, we don't care about other properties. So as long as the temperature is higher, then the kinetic energy must be higher also, regardless of what material we are talking about. Okay, so they are talking about that. And now let's move on. Absolute zero. Absolute zero means 0 Kelvin. 0 Kelvin. Temperature at which a system has minimum internal energy, which is not zero. Minimum internal energy. They still have potential and kinetic energy. That means you add potential and kinetic to get internal, right? So internal is not zero yet. Impossible to remove any more energy at 0 Kelvin. That means at 0 Kelvin, you still have minimum internal energy, but you can't decrease it anymore. Okay, so that is absolute zero. And triple point of pure water, temperature at which water exists as vapor, liquid, and solid. At 273.16 Kelvin, which is 0.01 degrees Celsius. Okay, so what is triple point? Triple point is something that maybe you could hardly imagine. They say water exists as vapor, liquid, and solid. So it seems like something that we don't see it. Water can exist as steam, water form, and ice form at the same time. Try to imagine, So it happens actually. We don't see because we do it on the earth. We do it at atmospheric pressure. Okay, so I show you how to make it. I draw a graph, pressure versus absolute temperature, and there are three lines which look like this. This region is solid, this region is gas, and this region is liquid. Okay, so how we understand it, for example, 1 atm is here. Okay, 1 atm, 1 atmospheric pressure. So we normally don't see triple point because our surrounding is 1 atm. 1 atm. So 1 atm, let's say, imagine I extend the line. Okay, I extend the line. So I have this point here. This point is what? It's a point between solid and liquid. Okay, this is the conversion of solid to liquid. It happens at this temperature. What temperature is this? Of course, we know it's 0 degrees Celsius. It's the melting point of ice to water. So that value have to be 0 degrees Celsius, 273.15 Kelvin. Okay, so then this point is where it is in between liquid and gas. So that is the boiling of water. So you should understand that this is 100 degrees Celsius. Okay, so then the temperature in Kelvin is 373.15 Kelvin. So we know this only normally, Normally we know this only unless you go and read a lot of encyclopedia. Maybe you heard before the triple point. Triple point is here, this particular point. So what happened here? This is triple point, the red point. Okay, so this red point is where at this particular pressure, that pressure has to be slightly lower than 1 atm, and the pressure is a little bit greater than 273.15. As you can see the notes, they said 273.16 Kelvin. So at temperature slightly lower than atm, and at pressure is lower, slightly lower, temperature is a little bit greater than 0 degrees Celsius, then at that specific temperature, then you can see water exists in 3 states. Okay, solid, liquid, and gas exist at the same time. Okay, so you can, of course, you can Google search, Google search the image to see how it looks like. So it just looks like ice and steam and liquid come together. Okay, so something like that. That is called triple point. We can do that in the machine actually. So that's why you can see the pictures if you go and look for it. Okay, but that is not our main concern. We just move on. 4.4. Practical thermometer. And this one is more important for exams. So we have two types of important thermometers here. Thermistor, and the other one is thermocouple. Thermistor, right? Thermistor, example, they use in fire alarm. Thermistor. Okay, thermistor. Let's see the advantages first. Advantages, or maybe we look at the common advantages. As you can see in the first row of the table, reading can be taken remotely for thermistor and thermocouple. That means you can just put the thermistor or thermocouple at a place which is out of human reach, and then you control it. You check the reading. At a far place. So it can happen. Now, for example, you want to check the temperature of the volcanic mountain. Let's say we want to check the lava over there. So you can't go there. It's too hot, right? So you can just maybe make use of a robot, or put inside the 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 thermometers, and then you can check remotely. Okay, so you can find out the temperature. Now, other advantages, very robust. Very robust. What I mean by that, very robust is like very perfect. Okay, very perfect. Very good. Perfect. Fast response. Accurate. Sensitive at low temperatures. Okay, so these are the advantages. And let's compare to this one. Thermocouples. Thermocouples, you should know. Just now I said thermocouples, we use two different metals. The basic structure is two different metals. Faster response. This is fast. This is faster. This is better lah. Seems like. Okay. So wider range. And seems like this is better than this. Small thermal capacity. Small thermal capacity means what? Means a little amount of heat can increase is enough to make changes in the EMF. Okay, small thermal capacity. Small amount of heat is enough to make change to the EMF. So smaller thermal capacity. And physically small. Okay, so reading taken at point. So for example, like in the handphone, you can, during, currently there are fast charging handphone. So fast charging is dangerous because it may explode because of high temperature. So because of that, they put thermocouple at different points of the electronic circuit board, so that they can check if any part is too hot, and then they have to turn off the fast charging. Okay, so automatically one. Power supply not need. That means you just put two different metals, then it works already. No need to connect to battery. No need lah. Okay, so thermocouple is basically, or you may easily find that this is better than thermistor. Okay, so disadvantages: non-linear variation with temperature. As you can see the graph that we draw just now, no matter uh, thermistor, of course, this one, the graph on the left, okay, they use resistance and temperature to work. Okay, so, and thermocouple, they use EMF and temperature to work. Both of these are not straight line graph, that is the disadvantage. Non-linear variation. This is linear variation. And this one, linear variation. Linear variation is easier. It's easier. So this one, you really need to look at the graph to find out, because they are not proportional one. They will bend one, they bend in a particular way. So that's the disadvantage. And now let's move on. Thermistor. Thermistor seems like having more disadvantages compared to thermocouple. Let's take a look. Narrower range. Okay, so narrower range compared to thermocouple, wider range. Slower response times. You see here they say fast response. This is faster response. So the slower response time is slower than thermocouple. Slower than thermocouple. Slower response time than thermocouple. Okay. But it is fast compared to clinical temperature, for example. You go to clinic and measure temperature, right? The doctor has to wait for a while. They will check other first. They put the thermometer under your armpit, and the traditional one, put under your armpit and check other things first before they look at your temperature. So that is slow response. This is fast. Of course, this is faster. Thermocouple is faster. Thermistor is fast. Now, next disadvantage: large thermal capacity. Larger thermal capacity, that means you need more heat to make the resistance change. More heat is required to make the resistance change. And larger in size, not suitable to measure varying temperature. Varying temperature means temperature that keep changing. So temperature that keep changing is not suitable, because they are not fast enough to show you the changes. The response is slower a bit. So if the temperature is keep changing, then it is good to use thermocouple. Okay, good to use thermocouple because it has a faster response. So a slight change, then the thermocouple will quickly show you, okay, there's a change in temperature, so we need to do something, like too hot, then you turn off, something like that. Too cold, then you heat up. So thermocouple can do that. And for accurate reading, a high resistance voltmeter is required. So as you can see, we need a voltmeter here to work out. Okay, thermocouple need a voltmeter to work out. So to make it more accurate, you need to use high resistance voltmeter. Okay, so